Hello and welcome to the first and only video in the M2 chapter Statics of Rigid Bodies. On the screen, an M1 question to review the chapter Statics of a Particle, which forms the foundation of this chapter. The box shown has mass 1 kilogram and is in limiting equilibrium on the point of moving up the plane. The phrase limiting equilibrium and on the point of moving give you the same information. The second part of the sentence is there because of the up the plane part. That's important. We'll come back to that later. So it's in limiting equilibrium, which means it is not moving, but it is just on the point of moving. Calculate the coefficient of friction between the box and the plane. In M1, there were two things to consider on questions like this. The first is that if the box is not moving, the resultant force in any given direction must equal 0, because if it didn't, it would move in that direction. The second thing is that the friction, which I'll use a subscript r so that we don't get those two confused, is equal to or less than mu times the normal reaction force. And whether it is less than or whether it is equal to is what this limiting equilibrium tells us. So in this case, this is actually going to be an equal sign. Considering these two things should allow us to solve this problem. To help us out, I'm going to put all of the forces on the diagram. We know that the box has mass 1 kilogram, acting vertically downwards. Now there are two forces on the diagram, and I'm going to split both of these into their component parts. So gravity, this way, is g cosine 40, and acting down the plane, the component of the weight is g sine 40 degrees. The pulling force up the plane is equal to 10 cosine 20 degrees, and perpendicular to the plane coming out this way, 10 sine of 20 degrees. Now we also have the normal reaction force going this way, which I'll call R, and that R is the same as this R in this equation here. But we also have friction, and that's where this phrase up the plane is important, because if it's on the point of moving up the plane, we know that friction always resists motion, so the friction must be acting down the plane. That's a very important thing to realize. So we've also got friction acting down the plane here. Now I have all of the forces in yellow on the diagram. I can create two equations, one for the forces parallel to the plane and one for the forces perpendicular to the plane, effectively using F equals ma, where a is equal to 0. So the resultant force in any given direction must equal 0. So if we go perpendicular to the plane first, we've got r plus 10 sine of 20 degrees minus g cosine 40 degrees, because that's going in the other direction, must equal 0. That tells us that r is equal to g cosine 40 degrees minus 10 sine of 20 degrees. Parallel to the plane, the equation we generate is 10 cosine 20 degrees if I take up the plane as positive, minus friction, minus g sine 40 degrees. Those three together are the resultant force. That also must equal 0, which tells us that friction is equal to 10 cosine 20 degrees minus g sine of 40 degrees. Now we can connect these two equations through this equation here, which is telling us that this friction must equal mu, the thing we're trying to find, times this, the normal reaction force. So if I jump into red here, we've got 10 cosine 20 degrees minus g sine of 40 degrees must equal mu times r, which is g cosine 40 degrees, minus 10 sine 20 degrees. And if I divide through to find mu on my calculator, I get 0.7579, but because I've used g as 9.8, I'm going to round that to two significant figures, 0.76. In this chapter, we only have one video, and that is to form equations to solve problems involving static, rigid bodies, very similar to what we've just done, but rather than a particle, it will be a rigid body like a rod or a ladder or something like that. In M1, as we did in the starter question there, we solved problems of static particles, and that involved resolving forces parallel and perpendicular to the plane and using the friction equation. We did both of those on the starter question. These are the two equations that we used. And remember that static means in equilibrium and not moving. So for this equation here, unless the particle is in limiting equilibrium, then the friction is less than mu times r, and you have an inequality. If you're told it is in limiting equilibrium, that's the only situation you can then put an equal sign. Thinking beyond this chapter, obviously if the object is moving, then this is also true of a moving object, but in this chapter everything will be stationary. So you can only use this as an equation rather than an inequality if you're told it's in limiting equilibrium, or another way of saying that, on the point of moving. All of this should be familiar to you from M1. In M2 we take this a little step further and we look at static rigid bodies. And when we look at rigid bodies we know something about moments. We know that a rigid body held in equilibrium has the sum of its moments about any point equal to 0. This is true as well as the other two considerations on the previous screen. So to solve these problems that follow, you will need to create a suitable number of equations, depending on how many unknowns you have, by considering some or all of the following three things. Firstly, moments about one or more points, resolving forces in one or more directions like we did in the starter question, a friction equation or inequality also like we did in the starter question. So we still need to be able to consider these two things, and now we're also adding in moments equations, because we're going to look at rigid bodies rather than particles. In these sorts of questions it's really very useful to have a diagram, to be able to draw all of the resolved forces on the diagram, and to consider very carefully which point you're going to use for any moments equations, because sometimes choosing a particular point can make the equation much more useful. I'm going to go through the two examples in the textbook, and then I'll go through a couple of exam questions, because there's a particular type of exam question that I don't think comes up very much in the textbook. Our first textbook example, a uniform rod AB of mass 40 kilograms and length 10 meters rests with the end A on rough horizontal ground. So here we've got friction. The rod rests against a smooth peg C, so here there is no friction, where AC equals 8 meters. The rod is in limiting equilibrium, so friction is equal to not less than mu times r at an angle of 15 degrees to the horizontal. I've said it a few times before, a good diagram will help us here. So we've got a uniform rod, AB of mass 40 kilograms. The fact that it's uniform allows me to put the center of mass in the middle of the rod, 40 g for the weight. Its length is 10 meters. End A rests on rough horizontal ground. So A is down here and B is up here. And there will be friction down here. But I'm not quite sure which direction that's going to act yet, so I won't put it on just yet. The rod rests against a smooth peg where AC is 8, so it's up here somewhere. This point we're going to call C, and that's 2 meters away from B, 8 meters away from A. An important point here about the smooth peg is that there is no friction, but there is a reaction force that will go perpendicular to the rod. I'll call that N because I'll have a reaction force down here as well, and I'll want to call that R to be consistent with the friction equation. So let me put the weight on here in yellow as well. I'll put the forces on in yellow. So there must be a reaction force at A, and that will be going perpendicular to the ground. This is the one I'm going to call R, but there must also be a friction at A, and to consider which way friction goes, think about which way the rod would move if there were no friction. In this situation, the rod is likely to move this way, sliding off the peg and falling down on the ground here. So the base of the rod wants to move this way if there's no friction, which means friction must be acting this way, holding the rod in place. So we have all of our forces on the diagram now, but N is not in the same direction as the others. We know this angle here is 15 degrees. That means vertically we're going to have N cosine 15, and horizontally this direction we're going to have N sine of 15. Part A is to find the magnitude of the reaction at C. That's N on my diagram here. So when you've got to this stage, then you need to be thinking we've got three different things we can do. we can form an equation with friction, we can consider moments, and we can consider resolving forces. If I resolve forces, I've got friction, which I don't know, and something involving N, which I don't know. We've got the reaction force, which we don't know, and something involving N, which we also don't know. So those two are not yet going to be all that helpful. So we consider moments. This is really a very powerful thing, because if I take this point here, R and friction both have lines of action through this point, so the distance, the perpendicular distance, is 0. So the moment of R and friction about this point will be 0. That means moments about A gives me an equation with just one thing I don't know. And actually, although I've gone to the effort of splitting this into two component pieces, for the moments equation, it's this one that's going to be more helpful, because from here, that will make the perpendicular distance of N this distance, which I know is 8. So with 3 different things to consider, to find N, there might be a bit of a thinking process to decide which one is the best one to start with. In this case, it will be moments, specifically moments about point A, so that these two do not enter into my equation. So for part A, that's what I'm going to do. I'm going to do moments about A. Anti-clockwise moments must equal the clockwise moments because it's in equilibrium. On the left then we've got our N force times by 8 meters. But that's not the only force. Although R and friction are not involved in this equation, we do still have the weight. I haven't mentioned that because we do know what the weight is. But it's not just 40g times 5, because we need the perpendicular distance, and the line of action of the weight is this way, so the distance we need is here. So on the right hand side of this equation, for the clockwise moments, we've got 40g as the force, and the perpendicular distance of that is 5 cosine 15 degrees. Now I can use g is equal to 9.8, divide everything by 8 to give us the magnitude of the reaction at C. That is 236.6 ... which I will round to 2 significant figures. Although if I need to use that in a calculation again, I will of course use the accurate answer to keep the accuracy. Now for part B, we need to find the coefficient of friction between the rod and the ground. To do that, we're using the friction equation. Friction is equal to mu times R. So of course we need to know both friction and R in order to find mu, which means I need this one and this one. Now that we know N, however, this is not too difficult. We go back to something we considered at the very beginning. Resolving horizontally, this must equal this, and we know what N is, so N sine 15 must equal friction. Great, that's our first one done. Making it clear for the examiner what I'm doing, I'm going to use a bit of a fancy R resolving to the right. And that will give me friction minus N sine 15 equals 0. So friction is equal to N sine 15. I won't write N out because it's pretty clear for the examiner that we know what that is. But we also need R. Now we've got resolving vertically, R plus N cosine 15 minus 40g must equal 0. So again, making it clear for the examiner, I'm going to resolve upwards as positive. R plus N cosine 15 minus 40g is equal to 0. Tells me that R must equal 40g minus N cosine 15. Putting those two together with the friction equation, mu must equal friction divided by R. So that's N sine 15 degrees divided by 40g minus N cosine 15 degrees. And I'm going to put all of that on my calculator, including this divided by 8 for N, in order to keep maximum accuracy. And that gives me mu is equal to 0.3748 ... And again, because I've used 9.8 for G, round that to 2 significant figures, 37. So I hope you can see that we've used all 3 ideas. And there was a bit of discussion at the beginning as to which one was the right one to use first, and it won't always be moments that you do first, but in this case moments gave us N, then resolving gave us 2 equations to use with the value of N that we found in part A, and then the friction equation brought those together to help us find mu. Example number 2. A ladder AB of mass m and length 3a has one end resting on rough horizontal ground. The other end B rests against a smooth vertical wall. Okay, so we've got rough horizontal ground, smooth vertical wall, and a ladder in between. So there will be friction on the base and not on the wall. A is resting on the ground, B is against the wall. The length is 3a, and it has mass m, which I'm going to assume acts at the center point. A load of mass 2m is fixed on the ladder at the point C, where AC is equal to A. So about a third of the way up. Here, this is 2m mass, and the distance there from A is little a. The ladder is modelled as a uniform rod. That's good, that means that my center point for the mass here was okay. In a vertical plane perpendicular to the wall. This very formal language here just wants to be clear that there's no element of 3D in this, it's all happening in the plane of the screen. And the load is modelled as a particle, so this is just a point mass, whereas the ladder is a rigid body. The ladder rests in limiting equilibrium, so we know that the friction is equal to, not less than, mu times r, and it's at an angle of 60 degrees with the ground. That's this angle here, 60. Question A, find the coefficient of friction between the ladder and the ground. So before we do that, let's finish putting on our forces. We've got a reaction force at B from the wall pushing this way on the ladder. Let me call that S. We've also got the reaction from the ground pushing up on the ladder here at A. Call that one R because this is where our friction is. So this is the reaction force that's going to go in here. And if it could, it would slide down, which means this base would slide out this way, but there is friction here, so that friction must be acting this way. And that's the friction in here. So these two are these two here in this equation, and this mu then becomes the thing that we want to find, the coefficient of friction between the ladder and the ground. Now the forces are all on. We need to consider our three different things. We've already got the friction equation here, but I think it's fairly obvious we can't use that yet. We don't know what R is, we don't know what friction is. How can we find mu if we don't know those two? So let's put that to one side and focus on resolving and moments. Resolving here is actually quite easy because all of the forces are already in two perpendicular directions. We've got friction and this reaction force here acting horizontally. So if I resolve to the right, friction minus S must equal 0. So the friction is equal to that reaction force S. So if we know one of these, we know the other. Resolving vertically, make up the positive. We've got R minus mg minus 2mg must equal 0. So R is equal to 3mg. Now those two are very simple equations. They're so simple that putting them together isn't going to help. We're going to need more information. This is where our moments come in. Looking then at my diagram, I would probably take moments about A. Although that takes friction out of my equation, it also takes this one out of the equation, and I know that S is equal to friction. So that would be the easiest way to find S, which gives me friction. I could also have taken it about point B to get rid of the S, which I don't really want, to find friction, but then I've got 4 terms in my equation instead of, from here, 3 terms. So we know it's in static equilibrium, so the anticlockwise moments must equal the clockwise moments. Anticlockwise around this point is just the reaction S, and the distance there is the distance of the ladder, 3a, times the sine of 60 degrees. That gives us S times 3a sine 60. Clockwise moments about A, 2mg times A cosine of 60. And also mg times 1.5a cosine of 60. All of the a's cancel, and then divide this side by 3 sine 60. And just to avoid writing that out, I'll take that off there and put it over here. 3 sine 60 degrees here. And that gives us the reaction S, which usually wouldn't be very helpful, but in this case it happens to be equal to the thing we want, friction. So friction is equal to this, and the reaction at A, down here, is equal to 3 mg. So mu is equal to friction divided by R, this thing, divided by 3 mg. So mu is equal to friction over R, which is equal to 2 mg cosine 60 plus 1.5 mg cosine 60, which I've just realized you can add together to make 3.5 mg cosine 60. I'll do that in a second. Divided by 3 sine 60, and also the R, which is 3 mg. So we can add the two terms in the numerator together and cancel all of the mg's, which gives us 3.5 cosine 60 over 9 sine of 60. And then if I put that in my calculator, we get 0.2245 dot dot dot. And although we haven't used 9.8 for g in this calculation, I'm going to round it, and I will do 3 significant figures. And that is the final answer for part A. Part B was mostly answered earlier in the video. State how you have used the assumption that the ladder is uniform in your calculations. Assuming that the ladder is uniform was the only reason that I could put the weight of the ladder at its midpoint. If the ladder is not uniform, then I don't know where the center of mass of the ladder is. And if I don't know where the center of mass of the ladder is, I can't do the question because we needed this distance here in the calculation here. So as usual, I won't write this out, but your answer would be, assuming the ladder is uniform, allows us to assume that the center of mass of the ladder is at its midpoint. Okay, that's it for the examples in the textbook. I wanted to do 2 exam question examples as well though, because of this phrase here, freely hinged. So here we've got a uniform rod AB of weight W, and again the fact that it's uniform means we can put W at the midpoint of AB. It is freely hinged at A to a vertical wall. So this is the key point here that I want to focus on, freely hinged. That's different to it just resting against the wall like we had with the ladder in the previous example. If that was the case, the reaction at the wall would be perpendicular to the wall. But it's freely hinged. That means it's sort of fixed against the wall. It can't move away from the wall, but it can rotate. So this angle potentially could be different. If we could hold B, pull it up, the angle would get smaller, pull it down, the angle would get bigger, but it would not be able to come away from the wall. The key thing to realize about this is that that means the reaction on the rod from the wall is not happening along a known direction. It is not necessarily coming out perpendicular from the wall. It is not necessarily acting along the rod. The reaction at A on the rod could be in any direction. So to deal with this, what I would do in this situation is put on a horizontal component and a vertical component of the reaction at A. Don't assume the direction unless you're explicitly told in the question. Okay, that's a lot of information coming off the first sentence, but that's the key difference between this sort of question and the previous questions. So the rod is supported in equilibrium at an angle of 60 degrees to the wall by a light, rigid strut CD. Remember that light means this bit here is modelled as having no mass. The strut is freely hinged to the rod at the point D and to the wall at point C, which is vertically below A as shown in figure 1. Okay, now we need to be a little bit careful, because although I just said about being freely hinged means you can't assume anything about the direction, this is a slightly different situation here. If you imagine yourself as the strut, you're wedged between 2 points, here and here. You can't move, and this bit here of course has gravity pulling it down, so there's a feeling of compression, and compression, like tension and thrust, always happens along the rod. So we need to be very careful with our forces here. The rod and the strut lie in the same vertical plane, which is perpendicular to the wall. Again, that's just formal language, making sure that there's nothing 3D happening here. The length of the rod is 4a, and AC equals AD equals 2.5a. show that the magnitude of the thrust in the strut is this. Okay, that's quite a lot before we get started, but the important thing is to get our forces on the diagram correctly, otherwise we might mess everything up. So going through it very carefully, we've got the weight of the rod that we're assuming, because it's uniform, is acting at its midpoint. So that's the weight here. The rod we know is 4A, so from A to here is 2A. We also know that from A to D is 2.5A, and so is A to C down here. Now the slightly unusual but very important points. At A, the reaction on the rod is going to have two components because we're not sure which direction that is acting. I'll call those R and S. And if we think from the point of view of the strut, there must be a compression force acting in this way along the strut. It can only act along the strut. That means the thrust is equal and opposite going out this way. So from the strut on the rod, there is a thrust acting this way in the direction of CD. Now we've got the forces correct, everything else becomes just as before. We've got three things that we should think about. Friction, in this case, doesn't apply, we don't have friction. So we've got resolving and moments. For part A, we want to know the thrust is some fraction of W, so we're not really worried about R and S at this point. We want thrust in terms of W, so probably I'm going to do moments about A. That will get rid of these two out of the equation, and just consider these two. So for part A, we're going to do moments about point A. It's all in equilibrium, so we know that the anticlockwise moments equal the clockwise moments. Anticlockwise about A, we only have the thrust. But remember, we need the perpendicular distance, so we can't just go, oh, it's 2.5A, it's not. The line of action comes back to here, and we want the perpendicular distance here. So we also want this. A little bit of angle manipulation tells us that this is 60 degrees as well. So this distance here is 2.5A, missing an A there, times the cosine of 60 degrees. So that's the perpendicular distance for the thrust. So thrust times 2.5A cosine 60 must equal the clockwise moments, and that's W. And again, it's not this distance, we want the perpendicular distance, so following the line of action and extending this out here, we find that this distance here is 2A sine of 60 degrees. So that's W times 2A sine of 60. The A's cancel, so if we divide through, we get T is equal to W times 2 sine 60 over 2.5 cosine 60. We just want a numerical answer for that. So if I put it on my calculator, we do indeed get 4 root 3 over 5. And that must be the magnitude of the thrust. Part B, find the magnitude of the force acting on the rod at A. And maybe you can see from the diagram why this is going to be 6 marks. Because this is not just finding one unknown, we're going to have to find two unknowns, the two components, and then put them together to find the magnitude of the single force. But again, now that the diagram is correct, all that we need to do is follow our usual process. Resolving forces seems like a sensible thing to do, because T has a horizontal and vertical component. Vertically, we've got this one, the weight, which we know is just W, and R, so we can find R. Horizontally, we'll have this component and this component, and straight away I can see that I've put S in the wrong direction. That's going to be a negative, because we can see T has a component this way, so S, in order to balance that, must actually be acting this way. So if we follow up with what I've just said there, we're going to resolve vertically, take up as positive. That gives us R minus W plus the component of T, and again a bit of angle manipulation, we can see that this is 30, so this is 30, and with the vertical that would be 60, so this must be 30, so we've got T cosine 30, and that must equal 0, so R must equal W minus T cos 30, and we know T is this, and if I multiply that by cos 30, I get 6 over 5. So that becomes W minus 6 over 5W, which tells you that I also had R in the wrong direction. minus W over 5. Interesting. So R should have been this direction, but that's okay because that's taken care of with the minus here. Resolving to the right, we've got S plus T sine of 30 equals 0. So S is equal to minus T sine 30, and we knew that would be a minus, that's not a surprise. And that gives us minus 2 root 3 over 5W. The magnitude of the single force then is found by squaring both of these, adding them together, and square rooting them. So we've got minus W over 5, and you'll have noticed, perhaps in some of my previous work, I don't always put the minuses in when I know I'm going to square it. But I have done this time. Square root that, and that all simplifies to the square root of 13 over 5W, which is the magnitude of the force acting on the rod at A. Fourth and final example is similar to this to reiterate some of the ideas we just talked about there. So we have a uniform pole, AB, of mass 30 kilograms. Again, uniform means straight away I can put that weight of 30G at its midpoint. It's got length 3 meters, smoothly hinged to a vertical wall at one end A. The pole is held in equilibrium in a horizontal position by a light rod, CD. One end of the rod is fixed to the wall vertically below A, the other end is freely jointed to the pole so that ACD is 30 degrees, AD is 0.5, as shown in figure 2. You can see that this is very similar, but one quick note on the language: freely jointed is just the same as freely hinged. So here we're trying to find the thrust in the rod CD. So we've got the reaction at A. Again, we don't know what this is, so I'm going to use two components. Again, we've got the thrust in the rod, which is the same as the thrust acting on the pole. And I'll change the weight here to match the other forces in red, 30G. So we've got our four forces on the diagram. Find the thrust in the rod, this is the one that we want. We're going to do the same as before, take moments about A. We've just got this one and this one. So for part A, we've got moments about point A. The anticlockwise moments just T times its perpendicular distance here, which is 0.5 cosine 30, and that has to equal 30G times 1.5. Rearranging that gives me an answer for T of 60 root 3G. Part B, we want the magnitude of the force exerted by the wall on the pole at A. Again, very similar. We need to find S and R, put them together. I'll do the same as before. We're going to resolve. So horizontally, we've got S plus T sine of 30, and I've done it again. I've put S in the wrong direction, possibly put R in the wrong direction as well, but that's okay. We'll get negatives. So that becomes minus T sine 30, which is minus 30 root 3G. Resolving upwards, R plus T cosine of 30 minus 30G must equal 0. So R is equal to 30G minus T cosine of 30. T cosine of 30 is 90G, so yes, this is negative 60G. So R is actually acting downwards and S is acting in towards the wall. The magnitude of that single force then is 30 root 3G squared, or minus, plus minus 60G all squared, square root that, giving 30 root 7 times G, which looks a little bit awkward. So if I put G as 9.8 and get a final answer out of that, we get 777.8 dot 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 to two significant figures, 780 newtons. Now we have a final part that we did not have on the previous one. The rod CD is removed and replaced by a longer light rod CM, where M is the midpoint of AB. So instead of going from C to D, it goes C to M like this. The rod is still freely jointed to the pole, but now at M, the pole AB remains in equilibrium in a horizontal position. So nothing else changes, we've just got rid of this one, and replaced it with a longer one. Show that the force exerted by the wall on the pole at A now acts horizontally. So what we're showing here is that R is equal to 0. And what we could do here is go through the whole process all over again very quickly using T over here now. We could use the original triangle here to calculate AC, and then use that to calculate the new angle, go through this process here and find that R is equal to 0. And I'm sure if you did that and you showed R is equal to 0, there would be no problem. You would get 2 marks for that. But just 2 marks suggests that there is an easier way. And to show an easier way, I will put the forces on in purple. So ignore all of the red forces. So we've got the force from the strut this way now, the weight still acting this way. R we should allow for, although we know it should be 0 in this situation, and S here. The key difference between the two situations that really helps us here do this very quickly is if we take moments about this point, we can see that T, the line of action of T, now goes through this point, so this would have a 0 distance. That would not be included in the equation. Same with the weight, and same with S, whether it's coming this way or going this way, the line of action goes through this point, so all three of these would have a 0 distance in our moments equation about this point, which means the only force would be R, and for there to be only one force and no moment is impossible. R must be 0. So for part B, we would take moments about the point M here, where the anti-clockwise must equal the clockwise, and there are no anti-clockwise moments, and the only clockwise moment is R times 1.5 meters, so R must equal 0. And I hope you agree that that is a much quicker and easier way than redoing all of this. It also shows the power of choosing a good point for taking moments. In previous examples, sometimes it didn't matter, sometimes it did, sometimes it made the equation slightly easier, but here it makes the equation really, really easy. So if you need a moments equation, just pause for a second and think about the best point to take moments about, remembering that any forces with a line of action through that point will not be included in your equation. I hope that's enough now for you to have a go at exercise 6a. There's also a chapter review exercise for chapter 6, even though there's one section, and then there's review exercise 2, and the final thing in the book before the answers is the practice paper. And just maybe I'll see you for M3.